Sertraline is an antidepressant of the selective serotonin reuptake inhibitor, or SSRI type. It was first presented in a 1984 paper on non-tricyclic antidepressants by Willard M. Welsh of Pfizer, before being approved in 1991 under the brand name Zoloft. As of 2016, it is the most prescribed psychotropic medication in the United States. In this video, I will be conducting a total synthesis of sertraline. The catalysts I used in this synthesis are sensitive to oxygen and moisture. Therefore, I conducted the reactions under dry nitrogen using the air-free techniques developed by Wilhelm Schlenk. To replace the air in a flask with nitrogen, the flask is connected to a vacuum pump. This results in bubbling as dissolved gases come out of solution. The flask is then refilled with low-pressure nitrogen. A Schlenk line allows these connections to be made easily and through the same hose. I began by adding 21.62 grams of 1-naphthol to a Schlenk flask, followed by 140 milliliters of 1,2-dichlorobenzene. I closed the flask with a septum and stirred it to encourage the naphthol to dissolve. Some heating was required. Using the Schlenk line, I replaced the atmosphere in the flask with nitrogen. With a slight positive pressure of nitrogen, I passed a cannula, a long double-ended needle, through the septum. I then put the other end of the cannula through a septum on a flask containing 57 grams of aluminum chloride, a moisture-sensitive catalyst that was transferred into the flask in a glove box. By opening the aluminum chloride flask to vacuum, the naphthol solution is drawn into it. This is called a cannula transfer. The reaction produced a striking red color, a good sign that something was happening. The reaction begins with aluminum chloride being attacked by the naphthol on the para position, converting the hydroxyl into a protonated ketone. Dichlorobenzene attacks on the electron-deficient segment of the ring and displaces the aluminum chloride, which moves to the nucleophilic carbon on the dichlorobenzene. Aluminum chloride detaches and a series of hydride shifts balance out the remaining charges. This produces the first intermediate, 4-tetralone. I heated the reaction to 100 degrees Celsius for 1 hour. 70 milliliters of concentrated hydrochloric acid was poured over 240 grams of ice. I poured the contents of the reaction over this mixture of ice and acid. The ice quickly melted in the highly exothermic dissolution of aluminum chloride. The mixture separated into an upper aqueous layer and a lower dichlorobenzene layer. At this point, I was concerned about chunks of aluminum chloride that were under the dichlorobenzene and were not getting hydrated. Therefore, I placed the beaker in an ice bath and stirred it to keep it cold until all the aluminum chloride dissolved. I extracted the aqueous phase with 2 100 milliliter and 2 50 milliliter portions of dichloromethane, also called DCM. I washed the combined extracts once with water, producing a bright orange color. I clarified the organic extract with 10 grams activated carbon and 20 grams sealite, a fine silica powder. Both have extremely high surface area and absorb impurities before being filtered off. Sodium sulfate was also added to dry the extract. I filtered the extract and washed the flask and filter cake with more DCM. I used a rotary evaporator, or rotovap, to remove the solvent. A rotovap applies a vacuum to the mixture while heating it gently, which results in rapid evaporation at a relatively low temperature. The rotation of the flask increases the surface area available for evaporation and reduces the risk that the solvent will suddenly boil and spray into the condenser. The rotovap was very effective at removing DCM, but the vacuum didn't get low enough to remove all of the dichlorobenzene. To remove the dichlorobenzene, I used vacuum distillation. I attached the apparatus to the Schlenk line, which had a very good rotary vane vacuum pump. I was able to get the pressure low enough that the dichlorobenzene boiled well below 100 degrees Celsius. After evaporating the remaining solvent, I was left with a dark brown oil, to which I added 44 milliliters of methanol. When I turned on the stirring, the layers mixed and all of the 4-tetralone precipitated out of solution. I filtered off the methanol but struggled somewhat with getting some of the larger chunks of crystals out. I washed the crystals with more methanol. After letting them dry, I got a yield of 24.7 grams, or a percent yield of 56.5%. The next reaction converts the 4-tetralone into sertraline 1-imine. It begins by dissolving 13.5 grams of 4-tetralone into 140 milliliters of toluene. I removed the air and replaced it with nitrogen and chilled the solution in an ice bath to improve the solubility of methylamine. Methylamine is the simplest alkylamine and is the most difficult molecule I have worked with thus far. It boils at -6 degrees Celsius, is somewhat toxic, and possesses a stench that is best described as thermonuclear litter box. For the immunization, I had to add liquid methylamine, which I'd previously condensed using dry ice and acetone. I was planning to use another cannula transfer with the methylamine flask on a scale to measure how much I actually transferred. Shortly after I started the transfer, the odor of methylamine reached my nose. I was so focused on getting the transfer done without injuring myself that I knocked the camera away and lost the rest of the shot. My plan to measure the amount added with the scale also failed. However, the methylamine was to be added in excess, and I know that I added an excess based on volume. Titanium tetrachloride is a hard Lewis acid widely used as a catalyst. It is an inorganic liquid that reacts violently with water to produce hydrochloric acid and titanium dioxide, which forms a white smoke in air. Historically, it was used to create smoke screens in war and special effects. The titanium tetrachloride was delivered in a bottle with a septum, and a syringe was needed to access its contents. I purged a syringe with nitrogen repeatedly and then filled it with 3 milliliters of nitrogen. I withdrew 2.6 milliliters of the titanium tetrachloride. When I started the addition, the smoke in the flask looked so interesting I decided to lower the ice bath. This was a mistake. Regardless, this addition was among the most beautiful reactions I've ever done. After a short time, the color dramatically changed into a dark brownish green, which was much less exciting than the brilliant red. I left the reaction to stir overnight, or about 17 hours. The ketone in 4-tetralone attacks the electron-deficient titanium tetrachloride. This forms a carbocation which is attacked by the lone pair in methylamine. 2 chlorines then accept protons, becoming hydrogen chloride. The carbon-oxygen bond breaks, forming titanium oxychloride and sertraline 1-imine. The titanium oxychloride can catalyze one additional immunization, being completely dechlorinated to titanium dioxide. The next morning, when I removed the septum, the contents of the reaction bubbled over like a soda. I think the methylamine suddenly came out of solution when I relieved whatever pressure was inside the flask. I filtered the contents of the flask to remove titanium dioxide, but some still got through. The remaining toluene was removed with the rotovap, producing 12.5 grams of pale yellow solid. This represents a yield of 88%, identical to the yield presented in literature. I added 6 grams of the imine to a Schlenk flask and dissolved it in 100 milliliters of methanol. I then added 0.75 grams of palladium on carbon and sealed the flask. I used the Schlenk line to replace the atmosphere with nitrogen and then evacuate the flask. It was really important to remove all the oxygen from the flask because hydrogen is extremely flammable, and palladium on carbon, when saturated with hydrogen, can spontaneously combust. I attached a balloon containing hydrogen to the evacuated flask. Opening the stopcock filled the flask with hydrogen. I left it to stir overnight. The next morning I removed the balloon, almost forgetting to close the stopcock. Fortunately, nothing caught fire. I used the Schlenk line to remove residual hydrogen and refill with nitrogen. The inverted funnel is venting a stream of nitrogen to prevent the pyrophoric palladium on carbon from catching fire. I filtered the reaction and washed everything with methanol to recover as much product as possible. I transferred the filter paper to a jar that I had purged with nitrogen so it wouldn't catch fire. I rotovapped off the excess methanol. The residue was dissolved in a mixture of water and diethyl ether. There was a white precipitate that dissolved in neither, most likely titanium dioxide that got through the filter earlier. This clogged the funnel and made the liquid-liquid extraction difficult. I dried the ether extract with anhydrous sodium sulfate and removed the ether with the rotovap. This oil is the final product of freebase sertraline. I produced 4.9 grams of it, or 81% of theoretical. If I wanted to have a more pure product, I could run column chromatography. However, it was pure enough to do NMR on. Thank you for watching and have a good one.